In the past 4 years, there's been explosive growth in mobile IP usage. ITU ICT statistics report that in the period from 2000 to 2010, the number of mobile cellular subscriptions has increased by 8-fold, a rate that astonishingly exceeds the growth in the number of internet users over the same period. The dominance of mobility is given further perspective by comparing it to trends for fixed telephone line subscriptions, which continue to decline, and as 2010, there were 4 times more mobile subscriptions than fixed line. The introduction of smartphone and tablet technology has fundamentally changed the way we do business, spend our leisure time, and interact with our family and friends. There's a symbiotic connection between the capabilities and business models enabled by smartphones and tablets, and the cellular network that is the anchor point to the internet. Each one feeds off the other. As smartphones and tablets become more capable, people figure out new ways to exploit the capabilities, stressing network capacity, marketplace dynamics engage, and network operators respond with network upgrades. New mobile smart devices are introduced that consume the new capacity, and so the cycle continues, with analysts painting a picture of a network in 2020 needing to support a capacity that is 1,000 times greater than the network of today. One of the key challenges we face in the wireless industry is extending capacity. Shannon's famous channel capacity formula informs us that bandwidth efficiency can only be improved at the cost of reduced power efficiencies. Capacity is a linear function of bandwidth, but a logarithmic function of signal-to-noise ratio. This has led the research community to invent increasingly effective ways to use bandwidth within a complex set of constraints involving regulatory requirements, considerations for spectrum licensing, interoperability, multiple access, reliability, quality of service, and spectral flexibility to the level of each individual UE. These are some of the motivating principles that have led to MultiCarrier Modulation scheme and evolved packet core employed in LTE, and they continue to be motivators for features such as carrier aggregation in LTE Advanced. But relying on channel bandwidth alone to address the capacity challenge is not enough. Further capacity improvements have been made possible through the use of spatial division multiplexing MIMO. While SDM can be employed to increase the throughput for a single user, spatial division multiple access configurations can maximize the number of supported users in a cell by sharing the total system throughput between the users. MIMO transceivers, together with distributed or virtual MIMO, have permitted power-efficient or green solutions to the capacity problem. As we move to LTE-B, it is possible, more likely, probable that 3D MIMO, or full-dimension MIMO, will be embraced by both a future version of the 3GPP standard and by OEMs building macro base stations. Heterogeneous networks and beamforming small cells offering vertical and horizontal electrical beam tilt will be deployed to address coverage holes and minimize intercell interference. The rich set of concepts captured under the umbrella of self-organizing networks is one of the must-have technologies on the LTE roadmap. There are multiple facets to SON: automatic neighbor relations, load balancing, traffic growth and capacity management, self-optimizing, self-healing, energy savings, coverage considerations, and LTE parameter optimization. Another key aspect of SON is by making the network smarter, with the goal of minimizing OpEx-related drive tests. To improve the networks, operators often deploy engineers in the field to collect radio measurements, to discover problems such as coverage holes in the network. However, such conventional drive tests are expensive, and the collected measurements can only give a limited view at one point in time of the entire network. These problems have been actively discussed in the Next Generation Mobile Networks Alliance and in the 3GPP organization. The answer to these dilemmas is digital signal processing. A mid-range, all-programmable device like the 28nm Xilinx Kintex 410T with 1540 multiply accumulators operating at 491.52 MHz can deliver a peak compute of 757 billion max per second, a 300,000-fold increase over that of the first generation of Harvard architecture integrated DSP processors released in the early 1980s. This DSP compute power can be used to implement advanced crest factor reduction, to control the peak-average ratio of a transmission waveform, and to apply digital pre-distortion processing to linearize a low-cost, highly nonlinear Doherty power amplifier. This allows designers to control the overall cost of their equipment by defraying some of the high cost associated with building high-fidelity RF processing and amplification to the relatively low-cost world of digital signal processing, which, unlike the former, has been able to benefit from Moore's law process node scaling. As we look to the future, it is easy to see that radio processing is going to become more complicated, and we note the wide range of carrier configurations that need to be supported. As an OEM, one is left with the dilemma of needing to rapidly build a suite of cost-effective solutions that can capture the frequency planning requirements of a network operator. These requirements are a complex equation based on the parameters of spectrum licensing, spectrum fragmentation, and the need to support multiple radio access technologies from a single RF chain, the multi-rat challenge. We're also talking about heterogeneous networks comprising a mixture of macro base stations, small cell underlays, and Wi-Fi offload. It's a question of scale and flexibility, two properties at the very heart of Xilinx, all programmable SoCs and FPGAs.